Okay, in this video I'm going to talk about some exercises from 9.4. The first one I'll look at is 9.4.4. This one is to prove or disprove that, first of all, that GL2 of R is a subgroup of M2 of R. Let me talk about this one. Now, to be a subgroup, it must have the same operation. So here we have M2 of R. This M2 of R is under plus. So what you're asking about is GL2 of R a group under plus? So that's really the question. Is GL2 of R a group under plus? Now GL2 of R is the invertible 2 by 2 matrices. It's certainly a subset of M2 of R, which is the set of all matrices. But the question is the set of invertible 2 by 2 matrices closed under plus? In other words, if I take two invertible matrices and add them together, is it still invertible? Okay. All you need to do is find one counterexample to show that it's not true, and if it's not true, then it's not a subgroup. All right. Same for UN. Zn is a group under plus, so all you need to do is show that U of n is not closed under plus. In other words, two units, when you add them together, is not necessarily a unit. Now remember, unit means an invertible element of Zn. So, for instance, in Z4, 3 is an invertible element, but 2 is not. And we're talking about inverse under multiplication. So the thing is that when you're doing these problems, the operation you need to look at is addition. Even though ordinarily these groups are thought of as multiplicative groups, we're asking whether they're subgroups of additive groups. So you have to look at these sets under multiplication and just show that they're not closed. I'm sorry, you have to look at these sets under addition, and you have to show that these sets are not closed under addition. All right, let's look at 9.4.5. Here you want to prove, suppose G is a group with identity element E, and let H be a subgroup of G with identity element F, then E equals F. Now, as I note here, you need to be careful. You might think that this is something you just assume, but it's not something you can necessarily just assume. It has to be proved. In particular, it's not automatically obvious that E has to be in the subgroup. E could be an element outside the subgroup possibly, in which case it wouldn't be the identity of the subgroup. So that's one of the things that we're going to have to show. All right, so so here's one way to prove it. You can follow this outline, or you might have another way of proving it. So given any h in little h and big H, any little h was an element of big H, consider HF and HE. Now you can show that HF equals HE by using properties of identity. Notice that F is an identity in H, so you can use the identity property of F here, and E is identity in G, and H is in G, so I can use identity property here. Now, since H is in the big group, H must have an inverse, H inverse in G in the big group. Okay. Now, if you have an inverse H inverse in the big group, then you can think about what H inverse H must be. Remember that E is the identity of the big group. All right, so since H has an inverse in the big group, you can apply H inverse to both sides of this equation, HF equal HE, and then figure out what you get. All right, and that's going to be a way of showing that these two identity elements are equal. All right, there might be another way. You might be clever and find a better way. So I'd be interested to see other proofs if you can come up with another proof. All right, last one. Here the set T is defined as a subset of C whose elements all have modulus of 1. This is actually the unit circle in the complex plane. All right, if you draw the complex plane and you take the real part and the imaginary part, all the elements of modulus 1 are going to lie on a circle. And if you remember complex multiplication and you multiply two elements on the circle, it's just like adding the angles. All right. So there's a proposition to prove that T is a subgroup of C star. I was going to focus on this part C, prove or disprove that T is commutative. Now, this is an example of what's called an inherited property. So this should not be a complicated proof. But the thing is that if you have a large set that's commutative, then any subset is also going to be commutative. So I write that out down here. Suppose G is a group, and H is a subset, not even a subgroup, but a subset of G. If you have two elements of H, then those two elements are also in G, right? Okay. All right. Now, since G is commutative, you can conclude something from that because H1 and H2 are also in G. Okay. And since H1 and H2 were sorry, you can't see this. Okay. Okay. Now, since H1 and H2 are arbitrary elements of H, and we show the commutativity property for them, then we can show that H is commutative. All right. So, as I said, this is an inherited property. You may see other inherited properties, for instance, associative, identity, inverse. Well, identity is kind of an inherited property. You have to make sure that the identity is in the subset. Inverse is not. Well, identity and inverse are a little bit problematic because of closure, but the commutative and associative definitely are inherited properties. So that's kind of automatic when you have a large set that's commutative or associative. Any subset or any subgroup is also going to be commutative or associative. All right, so that's it.